In the circulator amplifier shown here, we have a cap connected between port 2 and 1, and somehow the feeling from port 3 with respect to 1 is as if we have an inductor. Is this true? If this is true, it means that this circuit can effectively work like an impedance converter because it is converting a capacitor into an inductor, and it has a lot of practical application because if this is true, it means we will be able to realize potentially high value inductors with high quality or high Q that practically would be either super difficult or impossible in some cases if we were supposed to have an actual passive inductor in the circuit. So there are a lot of potential applications for this as long as we can keep the circuit stable. Okay, so let's see. One thing I'm going to rely on is the well-known relationship between the ports of the circulator amplifier that is like this. Each port current is related to the voltage difference of the two other ports. Like I1 is V2 minus V3 divided by R. R is the constant value of resistor across the circulator amplifier, which is the parameter of the circulator amplifier. Let's say this is true. I have proved these three relationships in a separate video, but you can watch that. But I'm going to prove it again at the end of this video. But let's say these are true. Now I am interested in to see whether this statement that this circuit is converting cap to inductor is true. What I need to see is what is V3. So what is V3? What is V3 versus minus V1? That is what I'm interested in. What I'm seeing between port 3 and port 1. Okay, so V3 minus V1 according to this relationship of circulating amplifier is R times I2. So that I have. Okay, great. Now, but at the same time, for I2, it's the current that is passing through this cap. So naturally, it's a function of the capacitance, capacitor inductance, which is, sorry, capacitor impedance, which is 1 over Cs, and the voltage difference on this cap, which is V1 minus V2. So the voltage difference on this cap is V1 minus V2, as you can see, cap between port 1 and port 2. So therefore, I can say I2 is simply V2, V1 minus V2, the voltages on this cap divided by impedance of cap, that is 1 over Cs. So as a result, what I get is RCS times V1 minus V2. Great. Now, V1 minus V2 according to another equation from the circulating amplifier is R times I3. So this can be replaced by R times I3 using the third equation here. So I have RCS times R times I3. So summarizing, remember we started from the delta between V3 and V1 and we got to this point. Therefore, conclusion is V3 minus V1 equal to R squared, the parameter of the circulator amplifier, the value of the resistor throughout the circulator amplifier, R squared times CSI3 times CS and the whole thing times I3. That is exactly what I needed to prove. So what is this saying? It says the voltage delta that is observed between the voltages of port 3 and port 1 is equal to R squared times CS times I3, which is the current that is going that way. So that is exactly the meaning of floating inductance. This is a floating inductor, effectively, virtual one, that is realized because the way I'm seeing that V3 minus V1 is related to, say, I3 is as if I have an inductance with inductance value of L equal to R square CS, R square C, that's it. And therefore, the inductance impedance is Ls, which is R square CS. So that is what I'm seeing, and this is the proof of it. We are done in terms of showing that we actually have an impedance converter converting a cap to a floating inductance between port 3 and port 1. But now if you're interested, from this point on, if you're interested to see just a quick proof of this that I also showed in a previous video, imagine that port here we have V, let's say Z, and imagine here we have Vx at the output of the first op-amp and Vy, the voltage at the output of the second op-amp, and Vz at the output of the third op-amp that is copy-pasted through this wire back to the input of the circuit. Imagine that is the case. What I'm going to show you is a very quick version of what I showed in detail in a separate video, proof of these three important equations or relationships for a circulator amplifier, three-port current and voltages. So what I can write is this. Okay, so as I said, we are done with for the purpose of what this problem is asking. I'm doing an extra step. That extra step is this. I can say, because of virtual short that is valid for all these op-amp as long as they are properly biased and linear region not saturated, I can say V1 is here, that is connected, and V1 should be at negative terminal as well because of virtual short that says the positive and negative terminal of ideal op-amp should have the same value if the op-amp is in linear region. V2 should be the same as V2 here, and V3 should be the same as V3 here. Now, for each of these op-amps, I can simply say 2V1 equal to Vx plus Vz. So V1 is the average of Vx and Vz just because there is resistor R that has the same current that flows through it and then flows through this one. So the voltage drop across the two resistors R should be the same. Therefore, V1 should be midpoint between Vx and Vz, which is the meaning of this. You can extend this to all of them. So 2V2, 2 times V2 here is Vy plus Vx. So Vy plus Vx. And you can extend this to the third one. So 2V3 is equal to Vz plus Vy. So Vz plus Vy. Now, I can just, for example, compute the, let's name these, maybe this is the easiest one. Let's name this equation 1, let's name this equation 2, let's name this equation 3. And I can just do this game that, hey, subtract 1, subtract 2 from 1, so compute 1 minus 2, and as a result you get 2 times V1 minus V2 on one side, 2 times V1 minus V2 is equal to Vx cancel out from the 2 equation and Vz minus Vy. So Vz minus Vy. Okay, great. Now, one outcome here is Vz minus Vy is basically the voltage drop across these two resistors because they are in series effectively. The current flows through them in series. Nothing goes to input terminal of ideal op-amp. So therefore, Vz minus Vy is 2 times R times current, but that current is the same as this current, which is I3, because this resistor is R, this resistor is R, they have the same voltage across them. One side they both have Vy, and the other side they both have V3. So voltage drop across this R should be the same as voltage drop across this R. So the current should be the same. This should be I3. Therefore, Vz minus Vy is 2 times R times I3. So I'm going to substitute this guy with 2 times R times I3. And I'm done because 2 cancel out from both sides, and then you can see I3 becomes V1 minus V2 divided by R. I3 is V1 minus V2 divided by R. Exactly the third equation. You can play this game by doing subtraction of, say, let's say 1 from 3, subtract 1 from 3, and then you get the same thing, and you get to equation 1, and so on and so forth. So that's the procedure you need to do to prove these three relationships for the circulator amplifier that I used to prove this problem. I hope that this is helpful.